Hey everybody and welcome back. In this lesson we're going to be discussing absolute age dating. In a previous lesson we talked about relative age dating, and this was before we had any sort of understanding of isotopes and radioactive decay. But once we got into the 20th century and we discovered radioactive decay, it became possible for us to actually get an exact or very close to an exact age on rocks and minerals. So we're going to talk about that process a little bit today. I'm going to go over what isotopes are. I'm going to talk about isotopic decay and half-lives and what that means. We'll discuss different methods of radiometric dating, and I'll talk to you a little bit about the oldest crystal that's ever been found on Earth. All right, so let's get started with isotopes. So an isotope is a form of an element that differs from other forms of the same element because it has a different number of neutrons. Normally, we don't really talk about the neutrons in an atom. We typically talk about, we're really preoccupied with the protons and the electrons, and we don't really give a lot of thought to the neutrons at first. But it turns out they're really important to dating rocks, dating anything, and radioactive decay. So it turns out that elements have all sorts of isotopes. Oxygen, for example, has a few common isotopes, including oxygen-16, which has 8 protons and 8 neutrons, while oxygen-18 has 8 protons and 10 neutrons. So that, again, that number of neutrons varies between the different isotopes of oxygen. A half-life is a term that you'll come across frequently when talking about isotopes or radioactive decay. And a half-life is the amount of time that it takes for 1/2 of the starting quantity of an isotope to decay. So you start off with a certain amount of an isotope, and a half-life is how long it takes for half of that to decay into what we call the daughter isotope, or the resulting isotope. So if we look at a diagram that sort of explains this concept a little bit further, I particularly like this diagram because it illustrates it using a crystal, and I love that. But obviously there are other applications for radioactive decay. This is just one application of this sort of system. On the left axis, you see percent of parent isotopes. So parent isotopes, that's the starting isotope. And the daughter isotope is what it decays into. So that's the resulting isotope. To understand radioactive decay, or to be able to calculate the age of something, you need to know the ratio between the parent atoms, or the parent isotope, and the daughter atoms, or the daughter isotopes. So you have to be able to count both of those and have a ratio of parent to daughter. And that's going to allow you to determine how long that item has existed. If we're talking about crystals, for example, that'll let you know when that crystal crystallized and cooled and locked in its atomic structure. So if we work our way from left to right across this diagram, you'll see that we start off with a crystal that is all parent atoms, all parent isotope. It starts off with entirely 100% parent isotopes. And then as time goes on, those parent isotopes decay into daughter isotopes. And so you'll see some red daughter isotopes appearing as time progresses. When you decay half of the parent isotope into daughter isotopes at 50% here, so the percent of parent isotopes is 50%, that is the duration of one half-life. Half of the parent isotopes have decayed. So that is one half-life. If you continue on to the second half-life, then you have decayed another half of the quantity left. So we're down to 25% of the parent isotope. And you can go on to a third half-life, a fourth, a fifth, etc. You'll notice that you technically never run out of parent isotope. This line is asymptotic. It never actually intersects the x-axis. So it's kind of interesting to think that they never actually decay entirely, theoretically. So there are some important things to note here. You have to know the quantity of both the parent isotope and the daughter isotope to produce that ratio. The system also assumes that no atoms have left the crystal. this becomes a problem if you're trying to date the outside of a crystal, because we know that that crystal can weather away and it can experience radiation and it can lose atoms over time. But if you're studying the interior of a crystal, it's safe to say that no atoms have left the center of that crystal. So that's a safe place to do these sorts of analyses. Let's discuss a specific type of radiometric dating. This is potassium-argon dating, where you start off with potassium-40, which decays into argon-40. This is a pretty common radiometric dating technique, especially in geoscience, because it uses potassium and argon, and potassium is found in a number of minerals. This method requires that you have a mineral with potassium in it, and one that you're already familiar with is potassium feldspar. That's that pink mineral that we see here in this granite. What's also nice about potassium feldspar is that it starts off with no argon in its crystal structure. So that potassium within the feldspar is going to decay into argon over time. And there's no argon to start off with, which is great. So your calculation is going to be more accurate. Potassium-40 has a half-life of 1.3 billion years, which also makes it a really good technique for dating old rocks. So here is an illustration here. This is a proportion of potassium-40 that remains in the rock. All right, so you start off with 100%, and then the age in millions of years across the bottom here. So if you if you study your rock and you analyze the isotopes in your rock, and you find that it's 95% potassium-40 and the remaining 5% is argon-40, then you can plot this up and determine that your crystal is nearly 100 million years old. That's essentially how this process works. There are some other methods of radiometric dating that we use in geoscience, including uranium-lead, which has a half-life of 4.5 billion years. It's quite a while. And it's useful for studying rocks that are, that range from 1 million years to 4.57 billion years old. It's important that these rocks have uranium-bearing minerals, obviously, or else you won't have any uranium to study. There's also an isotope system involving rubidium and strontium, and that has a half-life of 47 billion years. Kind of wild. But this tends to be a less precise method compared to others that are more frequently used. And then one that you may have also already heard of is carbon-nitrogen, or what we call radiocarbon dating. Maybe you've heard of this before. This system only has a half-life of 5,730 years, which isn't very long at all. And it's really only useful for dating things between 160,000 years old. So this is typically used on samples of wood or bone or carbonate minerals. It can be used on young sediments, but if you think about it, it's not particularly useful to rocks that are older than 60,000 years. So it turns out that radiocarbon dating, although it's great for things that were recently living or for pretty young sediments or young rocks, it's not super useful for the majority of rocks on Earth that are much older than 60,000 years. So I kind of want to wrap up our discussion of isotopes by talking about the oldest crystal that we've ever been able to find on Earth. This was work that was done by the folks at University of Wisconsin-Madison, where I went to graduate school. Go Badgers. And the people in the geoscience department there were able to find the oldest crystals that we know to exist on our planet. These are zircon crystals. Zircon is an extremely weathering resistant mineral that typically forms in igneous rocks. And it was found in the Jack Hills conglomerate in Western Australia. And this conglomerate, there's actually a sample of this conglomerate in the department at UW-Madison, and pretty sure it's under bulletproof glass, because this is a really cool sample, Anyhow, they used radiometric dating using uranium-lead decay, so uranium-238 decaying to lead-206. They used that isotopic system to determine that the oldest zircon that they found in this conglomerate was 4.4 billion years old. That is incredibly old, almost as old as the entire Earth itself. So it really gives us a glimpse into what Earth was like pretty shortly after it formed. And this was a pretty interesting finding because up until this point, we had thought that Earth was, kind of molten and there wasn't really a solid crust. This is during the Hadean, like Hades, fire, and, so our understanding of early Earth changed. By discovering this zircon crystal, we realized that, there were actually cooled solidified, there was cooled solidified crust on our Earth at that time. So this was a really big finding. I think this was back in 2013, 2014. So it was pretty exciting. They used a machine called a secondary ion mass spectrometer, or the SIMS machine for short. And they used that to count individual uranium and lead atoms. And that is an incredibly tedious process. But they made sure to count every single individual atom. So that is what we know to be the oldest crystal on Earth. But I want to ask you, why is the Jack Hill zircon the oldest crystal on Earth, but not the oldest rock? So think about the type of rock that the Jack Hill zircon formed in. The Jack Hills conglomerate. Think about what kind of rock that is. Okay, hopefully your brain has sort of grabbed onto the idea that this zircon formed in an igneous rock initially, but we found it in a sedimentary rock, a conglomerate. So where that zircon originally formed isn't the rock that we found it in. It had been weathered and eroded away from its initial rock into something new. So we weren't observing the oldest rock, the rock that the zircon formed in. We observed it later in a sedimentary rock. Overall, the sedimentary rock is much younger. So it's really important to consider what rock type you're actually dating, right? So if you're studying crystals within a sedimentary rock, you have to be aware of the fact that those crystals actually formed and crystallized in something older, in an igneous rock or a metamorphic rock. So just keep that in the back of your head. So in this quick video, we talked about isotopes. We talked about isotopic decay and what half-lives are. We talked about a few different methods of radiometric dating that we use in geoscience. And we discussed the oldest crystal on Earth and talked about why it's the oldest crystal and not the oldest rock. I hope that this video taught you a little bit of what absolute age dating is, and I'll see you in the next lesson.